Hey everybody, my name's Logan, and my term poster has to do with the cycling of phosphorus, specifically how it interacts with groundwater and with agriculture. So, phosphorus is a finite resource that we only get through mining. There's lots of studies concerning agricultural use and eutrophication, but they all focus on surface waters, not much on groundwater until recently. There are potential toxic effects and problems with aquifers delivering nutrient loads to lakes, rivers, estuaries. The government here in BC is very aware of this, and since 2019 has moved to introduce phosphorus management plans for farms above vulnerable aquifers, such as here in the Okanagan Lake Basin. So there is hope, though, because it seems as though if we just alter our standard agricultural practices slightly to a more holistic approach, we can reduce the use and groundwater transport of phosphorus, and new technologies can then come in and we can help us recycle it. So my question was, how does agricultural management of phosphorus alter losses to groundwater, and what are the biogeochemical ramifications? And some of the studies that help me make that question. So overall, what happens is you have in agriculture, you will apply fertilizers and pesticides continually, season after season, and the surface soils can become saturated with phosphorus. At that point, it can begin to leach into the groundwater. Factors influencing this include the soil type, size, depth, what other factors there, how much water is applied. If you have lots of saturated soils and lots of rainfall and irrigation, you're going to have lots of phosphorus that leaches into your groundwater. And you can see that some of the effects of this do change based on how you till the soil or fertilize it. So if you have an inorganic fertilizer, it is actually drastically reduced overall at depth. As well, if you till the soil, as in you actually go in there and properly treat the soil before you plant and irrigate, that will drastically reduce the content of phosphorus at depth as well, which will minimize the amount that can leach into groundwater. Now, phosphorus transports through groundwater, the flow path can be quite long, ranging from a couple years to thousands. So a study in Lake Simcoe in Ontario found that for a pathway, just an example pathway here, A, look at the side profile, look at all those elevations. The lower aquifers, 5 and 7, contributed, I think, over 50% here just for this particular exfiltration pathway to the lake. And that water was thousands of years old. You can start to see a bit of a problem here if we're feeding into this and it is all enriched in phosphorus and potentially with arsenic, because phosphorus can free up arsenic in soil. This is a problem that's going to be legacy. It's going to be here for a long, long time, and we're not going to be able to really rectify it. Another study of a eutrophic lake in Germany found that more than 50% of its phosphorus loading came from groundwater. The delivery speed from groundwater versus from the aquifer was found to be much higher, but that case was because the aquifer is replenished and not really capable of storing significant nutrients in itself. Because of that, if you look at an aquifer such as the one that's under Kelowna, where we have much more people, 200,000 here compared to the 6,000 that live in Lake Arendsee, Germany, you can start to see that the aquifer is going to be easy to deplete. You could easily refill and enrich it with different sorts of nutrients. There's a high seasonality component to this, more than likely due to the agricultural component. As far as transformation, orthophosphate is the most bioavailable form, but it can actually be absorbed to different metal oxide species such as iron, such as calcium, and that will help to transport it through the soil to the reactive interface in the sediments where it can be oxidized and release those phosphates once again. This is happening in greater portions in different areas with different conditions. There's also the factor I mentioned just briefly that phosphorus can actually release and enrich the concentration of arsenic or selenium in soils by outcompeting them for adsorption sites. Now, the remediation techniques that we have available, it is becoming increasingly economically feasible to recover phosphorus, typically in urban systems like wastewater and the like, and then you can use that, reapply it as fertilizer again, often with the help of those metal species I actually just mentioned. Now, the best thing to do is to improve our farming practices. That includes planting trees and grasses that aren't actually directly profitable, moving away from the monoculture model of farming. You can also incorporate different kinds of farming, including grazing, pastures, uh, different ways to cycle the phosphorus through the upper layers of the soil. So here is a little bit of a graph showing you different areas where they've implemented these better farming practices and reductions across the board of nitrates and of phosphates, some as high as 70 so percent, looking at the shade there. So typically, what you're going to see here is remediation of contaminated systems that are in water now is possible. but you can't immediately reverse eutrophication. It's just not there. So ideally, we reduce and improve the farming practices. So the key findings that I had to take away was the phosphorus leachate can find its way into groundwater and has unique mobility there. This is because of the long-term use of fertilizers. Groundwater can replenish aquifers and lakes with phosphorus and other nutrient-heavy waters at a rate that is a lot larger than we used to think it was. Continued heavy usage of these phosphorus fertilizers could have possible delayed effects from storage inside aquifers, and reducing the usage of fertilizers and adhering to these best practices is really the best way forward. So thanks.